Assalamualaikum and a very good evening. I am Muhammad Farid bin Muhammad Fariza from my group, here to present what a type of product chosen. So for our project, our group decided to design a drone, but not just any drone. We decided to design an agriculture drone, or so our group call it agri-drone. The parts and tools that we have chosen for the functionality of the drone is chosen carefully in the morphological graph for us to maximize the work efficiency. The drone that we designed for our project, called agri-drone, will hopefully be beneficial to countries that are facing problems regarding agriculture, such as lack of workers in the farm. For our project, we designed a drone with a lot of functionalities that can be used in the agriculture industry. We hope that this design will be a baseline for new technology to come in the future. Thank you.
Hi and Assalamualaikum. My name is Sharul Amir bin Abdul Majid from Group 2. For my part, I will talk about the improvement that have been made for our product. As we know, our group have decided to design an agriculture drone. There are some improvements that we have implemented in our final product. But before we begin or proceed to the improvement, firstly, we need to identify what is the common problem faced for the agriculture drone. First, when larger load is lifted by the drone, there is a possibility that the drone will fall due to the weight exceeding the safety limit. So, how do we counter this? We have decided to increase the number of propeller by 8, so it will be able to lift the pesticide tank and the whole body. Moreover, larger diameter of propellers to ensure that it will equal with the air contact. It will enhance flight efficiency and will be more stable while hovering. Forklifts will be used to create more thrust and maximize control on the drone. Secondly, only small amount of pesticide can be carried during the flight time of the drone. This will burden the user to keep refueling the container. The way we fix this type of problem is by increasing the size of the tank so that it will be able to carry more pesticide. The tank will also have aerodynamic shape. The reduction in drag force toward the tip of the tank will decrease the wind resistance. The tank will be attached with a pluggable tank clip. It will ease the process of refueling the pesticide. Thirdly, the landing gear is not able to support the structure properly due to the heavy weight since the pesticide tank has been added. For this part, shape of the landing gear will be semicircle to absorb the impact when landing the drone. It will prevent from landing gear to break during the landing process. There will be several holes designed at the landing gear so that the air can flow through the landing gear. It will reduce the drag force and the air resistance. Next, the drone can only fly for a short period of time. The user needs to keep recharging the drone every single use. To avoid such things, solar panel above the body of the drone will be added or implemented to ensure that it will be keep recharging during the daylight flight time. Despite of that, the battery will also be added to store the energy, whether from the solar panel or from the main charger. Finally, the farmer cannot be sure either the crop site has already been poisoned. Because of that, we have decided to add a 360-degree camera so that it will be broaden the view of the crop site. This will help the user because of the better view by spreading the pesticide to the crop site. So that's all from me. Thank you.
Assalamualaikum. Here I am Muhammad Shakilin bin Zakaria. I would like to present about the complexity of CATIA tool used in our product and our design process from the early phase until its current state. So to begin, as we are now using CATIA software version 5, we were able to build a 3D product design from the development of 2D sketching tools to complete the 3D models of the product. As we all know, CATIA software is very useful as it allows us to cover the entire design process life cycle, as it has a lot of useful features and advanced modeling feature, such as we are now implementing the feature of mechanical design, which are part design, assembly design, drafting, and so on. And also we are using analysis and simulation feature to do a finite element analysis. Throughout the process of completing this agriculture design, as expected, we are actually encountered a lot of complexity, and we need to figure out all tools usable that need to be used for this product. Such as in the part design feature, there are a lot of tools that need to be used, assembly design feature, analysis and simulation that related with all shear forces that applied to the product, and also the product load and stuff. We, as a group, have optimizing our teamwork and communicate among each other so that everyone must be full aware of how these products are supposed to be done. So first of all, to build this product, we need to precisely discuss and analyze why this product design is chosen, then followed by sketching the raw design of the product and make some improvement to fulfill this mini project objective. Hence, we need to make sure that every part of the design has the exact dimension, thus it makes it easier to assemble all parts to one product later in the assembly design tool in CATIA. Our agriculture drone has exactly 25 numbers of parts, so we need to make sure that all parts can be attached to one another. So here, we as a group have to decide each dimension and also the material used for each part, and also the number of parts precisely, so that we don't need to face any problem related to that in the future. During designing the parts, there are some complex parts in our products, such as designing a propeller, and the other one is designing a gimbal, as the design is a little bit complex than the other design, as we have to apply some icons that are not being taught in class, such as multi-section solid, as this part has in geometrical shape. Then, after all of the parts have been completely finished, we are using assembly design feature to attach all of the parts. During this process, in order to assemble, we have to use coincidence constraint, contact constraint, and manipulation to attach one part to another part. Finally, we are using analysis and simulation and generative structural analysis feature to implement all shear force that have been applied to this drone. This process can analyze its capability of the material used and decide whether it is compatible or not to the product. Then we can apply all the load that have been measured by using the feature of distributed force icon. So yeah, I think that's all that I have mentioned earlier is the complexities of the feature that we have been encountered throughout the process. So overall, the concept of our drone design is very suitable and compatible for agriculture industry right now, and it has a lot of functionality and improvement made to the product to overcome the problem that have been faces with the current agriculture drone design in the market. So I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Taufik and I will continue the presentation for the next part. In this part, I will explain on what analysis that we use to evaluate the post-processing result of our product. By learning the finite element analysis for MSc 435 class, we can use static analysis that we sure it is very important to determine either of part it is in a good condition or not after we apply a load on it. Thus, let me go through on how we apply the features to our product step by step. For the first one, we start by set up the material for each part, either it is PVC, plastic, steel or aluminium. By doing that, we can easily recognize then determine the masses of each part that we already designed without need to manufacture it first. We used to determine the masses of each part starting from the little one, which is a screw, until the biggest one, which is landing gear. As you can see, we construct the table to calculate the total masses of our part, then convert them in weight. This weight will be used to complete the static analysis and obtain the result condition of our product, which von Mises stress and translational displacement vector. For example, let's take one part as our reference. We consider to take landing gear as our reference, as it is the part that holds the most load in the static condition. Thus, by having the details result, we used to arrange the load at the right section. As you can see, the landing gear will be applied by two loads from different sections, which is top section and the bottom section. These two sections will hold two different values of load. By applying the load on each section, we will get two forms of a result, which is von Mises stress and translational displacement vector. Both of these results can be generated from the CATIA software after you compute it. As you can see, according to the von Mises stress analysis, we could identify that there is a very small little area that experiences the most stress with 6 0.91 times 10 to the power of 5 Newton meter. In this context, the red color area represents the maximum stress experienced by the part. The distribution of stress at the tip gradually decreased and could be seen by the transition of the colors from red to orange, yellow, green, and eventually to blue, where it has the least amount of stress. In reference to the analysis, it is clear that maximum stress at the top of the part dispersed throughout the whole body, leaving the body of the part to experience the least amount of stress. And the next one is the translational displacement vector. Similar to the von Mises stress, the center of the part experiences the most displacement as it is illustrated in red color with 0.242 mm at the part. This value, a little amount of displacement, can still be considered in a good condition.
Assalamualaikum warahmatullahi wabarakatuh. We proceed to the material comparison used in the learning gear and the road connector. So we first focus on the learning gear. We decided to compare two materials in learning gear which were plastic and steel. So based on the table shown here, we see that the density, yang the modulus and yield strength of steel is much more higher than plastic. So despite of those, we decided to choose the material as the material to be used in our component. So the reason behind this is to prevent our product from over-design with steel material, as most of our components are using the steel material compared to plastic. So from the cumulative obtained here, which is 49 Newton at the top section and 16 Newton at the bottom section, plastic materials, they can support the load without exceeding any yield point. So based on the observation made through the analysis, we see that the transitional displacement vector, which is a maximum value for the plastic, only 0.242 mm only. Alright, so by this displacement, we assume to be negligible for our product. So additional to that, the manufacturing process for the plastic is much more easier in comparison to the steel, where plastic uses injection molding while the steel is using casting process. So this is very time consuming for steel. So in terms of material cost, plastic is much more cheaper than steel, which can greatly reduce the cost of manufacturing the whole process. Alright. So now we then proceed to the road connector, which we compare to the materials as well. So the material we compare in this component are PVC and plastic. So each of these materials give a very significant difference in terms of density, yang modulus, and yield strength as well. So as you can see here, each of the values for PVC stated in the table shown is higher than plastics. So as for that reason, we chose PVC material as for material to be used in this component. So based on the value shown just now, we see that PVC is more suitable for our drone. So cumulative load obtained here at the mixed section 7 Newton, while 4 Newton at the both sides section. Alright, where both material can actually support the load support without exceeding the maximum yield point. But then we try to compare again, we observe the transition displacement vector for PVC is much more lower than plastic. So it can be observed by looking by transition displacement vector, which is the maximum value for PVC is only 0.0965 mm, while the plastic is only 0.134 mm. This means that this component will be hard to bend.